Hey, it's Dr. Cody Rawl with Tech for Psych. If you're watching this video, chances are you're curious how devices like this personal EEG device actually work. In this video, we're going to talk about the different electrode sensors on this device, how it gathers the brainwaves to produce an EEG signal, and then how the device filters and amplifies that signal to create the brainwaves that we can actually use to analyze. So how are personal EEG devices like this actually picking up brainwave activity? How are they picking up the electricity that comes from the brain? Well, it's estimated there's over 100 billion neurons in the human brain. And at any one time, they can be firing. So they're sending electrical activity down axons from one neuron to the other. And if enough electrical activity builds up on the outside of cells, devices like this can detect them. Typically, it happens with pyramidal cells. You got these big columns near your skull, and a lot of electrical activity can build up on the outside of those. In the past, we've had to use paste or electrolyte gel in order to get the energy to cross the barrier between your scalp and the electrode. And in medical grade devices, we still use this. It's called electrode paste. But the cool thing about these is that their manufacturers, their designers, claim that they've created dry sensors, sensors sensitive enough to pick up electrical activity without having the paste. And this has made the consumer EEG product possible. If you take a look at the Emotive Insight, for instance, what you see right here, this green part, is their dry polymer electrode sensor. Now they claim that it can pick up the electrical activity without wet paste. And in my experience, it's pretty good at it. These devices actually do pick up brainwaves. And we're going to talk about how these devices actually work. So before we dive into how these devices actually work, I want to talk about the electrode placement system. The electrode placement system is important because if you get different results with different groups, you want to be able to compare the results. That way, when you see a designation for an electrode, you know exactly where on the brain it's supposed to be measuring. So the international system is called the 10-20 system. And it consists of using measurements of the head. So you use anatomical landmarks like the nasium above the bridge of your nose. You use the inion, which is a bump in the back of your head. And also the periauricular areas above your ears. You measure that and then you break it down, and the electrodes are placed up around your head, either 10% or 20% away from each other. That's where the 10-20 comes from. Now when you look at the measurements, there's either a letter or a number. The letters correspond to what lobe of the brain the electrodes are supposed to be measuring. So you see an F, it's corresponding to frontal, T is for temporal, P is for parietal, and O is for occipital. The numbers are more arbitrarily placed. You've got odd numbers on the left and even numbers on the right. If you look at these personal EEG devices, they actually follow this 10-20 system. Say with the Muse, you've got these sensors on the front and you've got sensors behind the earpieces as well. So if I'm going to put this on, and the Muse website clarifies this, and I talk about this in my brain mapping video as well, the frontal electrodes are frontal polar. That's what you designate them as. And then the ones behind your ears are temporal parietal, and that corresponds to this corresponding brain areas. So the reason why I bring up the placement system is that when you look at brainwaves, you need to be thinking of combinations of electrodes, not single electrodes. I think the easiest way to think about these devices is to think about them as a simple circuit. If you go back to your college physics days, basically you have a positive end with a loop, some resistance, and then a negative end. And then within that is a battery, right? There's three different measurements in a circuit. There's voltage, there's current, and there's resistance. Voltage equals current times resistance. The easiest way to think about a simple circuit is a water analogy. So if you have two different tanks of water, one above the other, and you have a pipe connecting the two, basically the water tank that's high has a more potential energy. So that would be like a higher voltage in the circuit. The pipe connecting the two is going to have water running through it. The amount of water that's running through it is the current, and the width of the pipe is going to be the resistance. Obviously, the bigger the resistance, the smaller the pipe, the less the current. And the amount of water that runs through it is going to be the pressure difference between the two, and that's voltage. Now, voltage is measured in ohms. And with that circuit, what you're looking at is the active electrodes on these EEG devices is the positive end of the circuit. You're having electrical activity in the brain that's building up on neurons close to the scalp. And that electrical energy is influencing the electrons in the circuit of the device itself. As I said before in this video, any brainwave that you see on a computer is actually the comparison between two active electrodes on an EEG device. So let's take a medical grade device for example. I was trained on the Nexus system for neurofeedback. If you look at the Nexus system, an easy setup that they recommend is one active electrode on the forehead and then one reference electrode on the earlobe. So why the electrode on the earlobe? Well, on your earlobe there's hardly, if not none, electrical activity. So when the two leads feed into the box called the amplifier is looking at the difference between the electrode on your head and the electrode on your ear. Basically what's happening is the electrical activity in your head is causing alternating current, and that's changing the voltage difference between the active and reference electrode. That voltage difference influences the amplifier, so it feeds into this box that's taking the analog signal, which is the alternating current, and turning it into digital information. It's looking at the analog current and saying, okay, it's moving back and forth, this alternating current. I'm going to turn it into this system of ones and zeros, and then the computer takes a look at that and then graphs it as a EEG wave. So the different oscillations are actually voltage changes between the two electrodes. If you look at a circuit, you need to complete the circuit, right? The negative end, it's a ground. And often with the Nexus system, they'll just put the ground right on your head. So you have the active electrode on your head and then the reference electrode on the earlobe feeding into the box. The box is taking a look at that signal and then graphing out the difference between the voltage, and then the ground electrode, which is on your head too, is just completing the circuit so that the circuit can keep going and the box can keep analyzing the signal that's going on. And the box is kind of like the resistance in the simple circuit. It's reading what electrodes are coming through, how they're alternating with the current, and graphing that for our brain EEG wave. Now, if you look at these personal EEG devices, you can almost see a simplified version of that. This is the MindWave Mobile, and let me just put this on here. So as you can see, it's actually got its own ear clips here. So I'm going to put this on, and as you may have guessed, this electrode is active. It's supposed to be picking up the electrons that are coming from my frontal lobe on my brain, and it has a reference electrode in the earpiece. Now, the two signals are feeding in, and I imagine the amplifier is somewhere within here, within the headset, the actual computer chip that's reading the signals and completing the ground circuit. I'm pretty sure the ground circuit is actually in the earlobe itself. As you can see, it actually has both sides have electrodes. So I think one is being used as reference and the other as ground to complete the circuit. If you look at the Muse headset from Interaxon, it's got the same theory but a different setup. So this middle one is actually the reference sensor. If you remember on the previous device and on the medical grade device, the reference sensor was electrically null. But we actually talked about this in my neurofeedback training too. You can have a reference electrode that's either not reporting any electrical activity or a lot of electrical activity. And as you can imagine, this one right here in the middle, when it's on my head, right smack dab in the middle, it's going to have a lot of electrical activity. But no fear, right? We're just comparing the difference in voltage between two electrode sites. So if you compare one of the active electrodes to right smack dab in the middle, it's reporting the difference, you still get a brainwave, all is good. Apparently, these next two ones out are the ground electrodes, according to the Muse website. And then the further ones out are the two active electrodes on your forehead, the frontal polar electrodes. And then the Muse device is pretty cool. It's got this conductive rubber on the side of the earpiece here, which conducts electrical activity. So these are active electrodes too. They're the temporal parietal reference electrodes. So you've got your frontal polar and you've got your temporal parietal electrodes, and then of course you've got your ground and your reference electrodes as well. And putting on the device, you would hardly think it, but these active electrodes are picking up my electrical brain activity that's feeding into the amplifier. And I'm going to recommend a video that's actually really cool. It's from Adafruit, where they take one of these apart. And you can actually see in one of the earpieces the chip that's used as the amplifier. All the circuits are feeding in into the amplifier, the signal's getting converted, and it's going back to the ground electrodes. Pretty neat. So I'm going to recommend taking a look at that video. I'm not going to take apart my headset because I don't trust myself to be able to put it back together. And also, why would I do that when I can just watch the Adafruit video? So that's the theory behind these EEG devices. It's really a circuit. You have active electrodes that are feeding into a chip that is an amplifier that has to do different filters. So it filters out the noise within the room. And one thing that I didn't mention is anytime you're within a room or near electrical power grid or anything that's electricity, you're going to get pollution, electrical pollution. There's actually a band of electricity in 60 hertz range, which is 60 cycles a second, that often needs to be filtered out because it contaminates the EEG signal. Nonetheless, it goes into the amplifier. The amplifier increases the amplitude of the brainwaves that are actually coming from the device and tries to filter out all the junk, and then that gets put on the computer into a raw EEG wave. Now in the next video we're going to talk about how the raw EEG wave actually contains all of the information from the brain, depending on where it is on your scalp. But you have to break that down into digestible pieces to actually make use of it. So we'll talk about that in this next video, in which we actually break the brain waves down into their individual components. One last thing that I wanted to cover was the difference between unipolar and bipolar recordings. So remember when I took us through the 10-20 system, why it was important to know where the different electrodes were? Well, that's because you want to know, if you're comparing two different electrodes, what exactly you're measuring. So you can actually do unipolar recordings, which is what we discussed earlier. Basically, you have an active electrode somewhere on the head, and you have an inactive reference electrode maybe on the earlobe. And the difference between those produces a brainwave, which is called a monopolar reading. You can actually take two different active electrodes and compare the voltage differences between those and create what's called a bipolar reading. Now, both unipolar and bipolar readings are used all the time. And different combinations of electrodes on their head might show better brainwaves for certain things. So let's say that you wanted to take a look at attention. Well, there's a lot of brainwave activity in the frontal lobe, which is good for attention, and maybe it's better to use two different active electrodes than one active and one reference electrode for that reading. There's a whole bunch of different examples where that might be true. Now with these personal EEG devices, they could use any combination of active or reference electrodes that they wanted to produce brainwaves. I'm not sure exactly what combinations they use. That might be coveted information, I'm not sure. But you can use different combinations of electrodes to take a look at different frequencies at different areas of the brain for specific disorders. There's a lot of variability with this, which is why the information is overwhelming at times. But I just wanted to cover the difference between unipolar and bipolar recordings so that you understood what was going on there in case you ran into it.